Welcome to lesson 5.5, solving systems of equations algebraically. So in this lesson we're going to take our linear equations and our quadratic equations and look at them at the same time. Up until now we've just been looking at them separately and solving, but now we're going to take them at the same time, work them together, and solve from there. So you'll get to see some concepts that we've used before in our previous grades. Here we go. A solution of a linear quadratic system of equations is an ordered pair x, y that satisfies both equations in the system. The system may have 0, 1, or 2 solutions. So looking at these graphs, it's what demonstrates the possible solutions we have. So our first graph here has no solutions because our graphs never meet. They never intersect or meet in any points. There's a separation there. Our second graph here is a system that has one solution because our graphs meet at one point. They kind of just kiss, they just touch here at one point in there. Our last graph here shows the system that has two solutions because they meet at 2 points. They intersect. So the line goes right through the parabola and intersects at 2 points. So these are the three scenarios that we might see when we go ahead and solve algebraically our systems of equations. So let's look at an example. Solve this system. Y equals 1/3 x squared minus 3 and x plus y equals -3. So in order to solve a system of linear quadratic equations, we need to find the coordinate pairs x, y that satisfy both equations. Now, like we said, there might be 0, 1, or 2 coordinate pairs. So we do this by this method that you've learned before. You might remember it once we look at it, and it's called substitution. So in substitution, we're going to take one equation and set it equal to something that we can sub in to the other equation. So in this case, we're going to have our number one equation as y equals 1/3 x squared minus 3, and number two equation as x plus y equals -3. So in this question, I'm going to sub 2 into 1. But first I need to set it equal to something that I can substitute for. So I'm going to rewrite this as y equals -x minus 3. So that way I can take this and sub it in for this y over here. We're going to get -x minus 3 equals 1/3 x squared minus 3. This is where we collect like terms and solve for x. So we get 0 equals 1/3 x squared plus x, and our 3's actually cancel. Well, from here our quadratic can be factored. So we have 0 equals x onto 1/3 x plus 1, and hence from there we can see that our factors are x equaling 0 and x equaling -3. Setting each part equal to 0 and solving. Well, now that we have two values for our x coordinates, we need to find our y coordinates. So to determine y coordinates, we can sub back into an original equation. I'm going to use equation 2 because it was a more simple equation. So here I have an x of 0 plus y equals -3, hence y equals -3. So my one point is 0, -3. Then the other one was -3 plus y equals -3. y equals 0. So then the other point is -3 and 0. And hence, these two coordinate points here are the solutions to this system of equations. And we can see that we have two solutions, so they must cross at 2 points. Excellent. So there's another system of equations that we need to look at as well. They are going to be quadratic systems of equations. We no longer have lines in these systems. A solution of a quadratic system of equations is an ordered pair again that satisfies both equations in the system. So there we go, there's the similarity there. So now the system may have 0, 1, 2, or infinite solutions in this case. So looking at each case, we have a system that has 0 solutions. So again, it never meets. There's no intersection or meeting at a single point. There's a separation here. And then a system with 1 solution meets at 1 point. So like I said before, just kisses, just touches there. A system with 2 solutions crosses at 2 points here. So we can say it crosses at 2 points. And our last case where it has infinite solutions, this means that when we have our graphs, even though they look different algebraically, they are the same graph when we go ahead and draw them. Therefore, they're going to have the same points and hence an infinite amount of solutions. They are the exact same graph. Great. So those are our 4 possible solutions that we'll deal with when we have quadratic systems. Let's look at an example to see how it works. So, example 2, solve this system. Y equals x plus 2 all squared minus 1, and y equals x squared minus 4x minus 5. So you can see we have 2 quadratics here. And we're going to use the same method we did before, where we have our 2 equations, and we're going to substitute in order to solve for the coordinate points. So here, let's sub 2 into 1 and then solve. We're going to get x squared minus 4x minus 5 equals x plus 2 all squared minus 1. So let's distribute this out. We're going to get x squared minus 4x minus 5, not changing yet. And this factors out to x squared plus 4x plus 4 minus 1 on this side. Now we can go ahead and collect like terms. And we're going to find that our x squareds are actually going to cancel when we put them on the same side of the equal sign. And then we're going to have negative 4x minus 5 equals 4x plus 3. Solving for x, we get negative 8x equals 8. And hence dividing by negative 8 on both sides, x equals negative 1. So from here, I'm going to go ahead and guess that we're going to only have 1 solution since we only have 1 x coordinate value. But we need to find the y that goes with this x. So we need to sub back into an original equation to solve for y. So let's just say we get y x squared is 4x minus 5. Equation 2. Y equals then negative 1 squared minus 4 times negative 1 minus 5. Solving, we get 1 plus 4 minus 5, and we get that y equals 0. So our final answer here is the solution of -1, 0, and that is the only solution we found. So this quadratic system of equations has only one solution, so they must intersect only at one point, at -1 and 0. And we could actually go ahead and check that by plugging it into our graphing calculator and seeing that they only intersect at one point. So awesome work! And that wraps up what we're looking for Unit 5.